So today's speaker is Markus Fröb from University of Leipzig, and he's going to tell us about modular Hamiltonians, relative entropy, and the entropy-area law in de Sitter spacetime. Please.
Thank you very much for the opportunity. And if you have questions, please interrupt me at any time. I'm happy to answer them. So I'll talk about various things. First, a very quick overview about entanglement entropy in quantum mechanics and quantum field theory, and what are the main differences. And then I will talk about the framework that I use, which is Tomita Takesaki theory. Just a very quick overview. One of the main objects there is the so-called modular Hamiltonian. So I will present some examples and some recent ones that my collaborators and I computed. And then finally, I'll talk about de Sitter spacetime, apply the theory to compute relative entropy, and also think about what observers actually might see. Okay, so let's start with the first thing, entanglement entropy, quantum mechanics, and quantum field theory. So on very general grounds, entropy quantifies the amount of observation that an observer has access to. So in particular, if the system is in a pure state, then everything is known, so the entropy is zero. And if one has a generic state in quantum mechanics, which is described by a density matrix, then one can define the von Neumann entropy, which is given by this formula here. It's minus the trace of rho log rho. And since rho is a density matrix, so in particular, the eigenvalues are between 0 and 1, this is always a positive quantity. Now, a typical situation that occurs is that the system is actually in a pure state, but the observer has access only to the degrees of freedom in some region A. And then one can define the density matrix of the observer, so the one of the thing that the observer sees, by just tracing the pure state, ket psi brass psi, over the degrees of freedom of the complement region. This gives a density matrix, and the entanglement entropy of that separation of the system in the region A and the complement is just the von Neumann entropy of this reduced density matrix. So it's minus the trace of rho A log rho A. This is not the only entropy measure. So the other ones like Thales entropy, which depends on the parameter Q. So it's 1 over Q minus 1 times 1 minus the trace of rho to the Q. There's the Renyi entropy, which is 1 over 1 minus alpha log of the trace rho alpha. The nice thing is that in the limit where these parameters go to 1, either the Q for the Thales entropy or the alpha for the Renyi entropy, they both reduce to the von Neumann entropy. So in a sense, this is the most basic entropy measure. And why is it called entropy? Well, consider a system in a thermal state. That means that the density matrix has a thermal form. So it's 1 over Z times exponential of minus beta H. Beta is usually its inverse temperature. Z is the normalization constant to make the eigenvalues between 0 and 1. We can write it as exponential of minus beta F, where F is the free energy. And then it's very easy to see that the von Neumann entropy of this density matrix is just beta times expectation value of H minus F. So this is nothing else than the thermodynamic entropy. And this is where the name, or why it's a good entropy measure and why it works. Now, if you go to QFT, let's say in D+1 dimensions, then we have the problem that density matrices are a more formal object, and the trace, if you actually want to compute it, is infinite. And both things are due to the infinite number of degrees of freedom that exist in the QFT as compared to quantum mechanics. So what people usually do is they, of course, as we all know, one can regularize. So one puts the UV cutoff, say epsilon, and computes regularized entanglement entropies. And then the terms that typically come out, they admit an expansion in powers of the cutoff of epsilon. So the leading term goes like epsilon to the minus d minus 1. So if you're in 4 dimensions, that's epsilon to the minus 2. And then there are lower order terms. There's a logarithmic term, a finite piece, and some terms that vanish with epsilon if it goes to 0. And the functions that multiply these powers of epsilon, they are homogeneous, and they depend on the geometry of the boundary usually. So especially in 4D, the leading term, it's G2, epsilon to the minus 2. So that gives you the area law of the entanglement entropy. It's probably well known. Is there a question? No, okay. And of course, well, if epsilon goes to 0, this diverges. The source of the divergences are high energy vacuum fluctuations of the fields, which do not exist in quantum mechanics. So that means that if one looks at differences in entropies between different states, these should be finite, because the vacuum fluctuations, I mean, they're universal. And
are you guaranteed to have to never have an epsilon to the d term?
Yes. So the first one, well, guaranteed, I'm not sure, but probably not. I think in all examples that people have looked at, it's d-1. Does this answer the question, or?
Yes, it does.
Okay. Yeah, so in all examples, it's d-1.
Okay, and it's down from 2 by 2 from the spacetime volume.
Yes. Yes, as I said, one should actually, to get something finite, one should look at differences in entropies. That's also not always enough. So there are some special cases where even the difference of entropy might still have some divergent terms, some subleading divergent terms. But one thing that is essentially guaranteed to be finite is so-called relative entropy. Or if you're from quantum information, it's the Kullback-Leibler divergence. So it's almost like a difference, but it's not symmetric in the state. So the relative entropy S rho sigma depends on two density matrices. It's trace of rho log rho minus rho log sigma. So if it really were a difference of entropies, the second term would be sigma log sigma. But so the state rho, in a sense, is distinguished. And one can also generalize this like the von Neumann entropy. So there's something called the relative Renyi entropy, again, depending on the parameter alpha. One can add more parameters, so something called the alpha Z Renyi entropy or generalized quantum Renyi divergence. You see the formulas there. Again, in the limits where the parameters that these entropy measures depend on go to 1, one recovers the relative entropy. So in a sense, this is again the most fundamental measure of a difference in entropy between different states.
Actually, just to follow up on the question Denjo asked, are you assuming a certain kind of quantum field theory? For example, I think if there are non-local effects, there might be the possibility to have stronger than area law entanglement.
Yeah, so right. So I'm assuming a local quantum field theory, the usual ones that we know and love. Yes.
And any particular class of states or, I don't know, theories?
No, not the theory in particular. Of course, later on for the examples, there will be particular theories. And as a state, let's say we take anything that has finite energy with respect to the vacuum. This should encompass the class of states where these things are well defined.
Okay.
Okay. So then the second part, what are the tools that one can use to compute these things? And in particular, the one that I use is Tomita Takesaki theory. So let's get a bit more mathematical. What is the difference between quantum mechanics and quantum field theory from a mathematical point of view? It's the type of the algebras of operators or of factors of the von Neumann algebras. In particular, in quantum mechanics, it's usually of type 1, which means that traces are well defined. Whereas in quantum field theory, the algebras of operators are of type 3, where things diverge. And mathematicians have developed a theory to study the structure of von Neumann algebras in the general case, which is the Tomita Takesaki theory. So what one takes is well, I said von Neumann algebra A. So this is the subalgebra of the bounded operators on some Hilbert space. And in addition to this, one needs cyclic and separating vector omega. So for example, if one takes, say, a Minkowski quantum field theory, scalar field or fermion or whatever, then the Minkowski vacuum would be cyclic and separating. But one can take other states. As I said, finite energy excitations should also work. With this data, one defines the so-called Tomita operator, which is essentially a map that takes you to the adjoint. So given an operator in my algebra acting on the state, it sends you to the adjoint of this operator acting on the state. This is a nice operator. It can be closed. It's a technical condition. And analogous to the decomposition of a complex number into phase and modulus, for closed operators, there's a so-called polar decomposition, which means that one can write S as a product of two operators, J and delta 1/2. Delta is the analog of the modulus. It's called modular operator. It's positive. Well, there's a 1/2 here for historical reasons. And the phase, the analog of the phase is J. That's an antilinear operator. Antilinear because S maps things to the adjoint. And it's called modular conjugation. And with these objects, one can define a so-called modular flow. So, well, I've written down here what the definition is. Sigma S of A is essentially the conjugation of A with a complex power of this modular operator. And one of the results of Tomita Takesaki theory is that this is a flow on the algebra. So it maps any element A in the algebra into the algebra again. So it's some sort of internal time evolution where the Hamiltonian is log delta. I could write this as e to the is log delta. And well, there's some other characterizations of these objects if you don't want to compute this polar decomposition in practice, which might be very difficult. For example, it has been shown that the state omega that is defined by this vector is a thermal state, so it fulfills the so-called KMS condition. That means you take two elements A and B, two operators in your algebra. One of them you evolve with the modular flow. This object is as a function of the parameter S admits an analytic continuation into the complex plane. So one can send S to S minus I. And the KMS condition says that this analytically continued function is equal to the one with the operator switched. So this is something that if you write quantum mechanics and take a thermal density matrix, it just follows from the fact that if you continue the time evolution in the imaginary axis, you get an e to the minus beta h. So this is the analog of this in a general theory where you don't have density matrices. And some further properties of these operators are that they are, suppose J and delta 1/2, they map the algebra to the commutant. So all the operators that commute with my operators in the algebra A. Okay, a bit technical, but we'll see that these conditions are used later on. Now, we had one state, but since we want to compute relative things, we need two states.
Just for clarity,
so,
you haven't assumed that omega satisfied some cyclic property, have you? That the trace of
yes. So omega must be cyclic and separating.
Yeah, but so does that mean that your omega of AB is equal to omega BA?
No, that would be
that cyclicity. I didn't think it did.
Oh, sorry. Yeah. Okay, so cyclicity means that you can approximate any state in your Hilbert space.
Exactly. Yeah, with the von Neumann condition. But
exactly. Mm-hmm. It doesn't mean that it's not the same as cyclicity of the trace. No.
Yeah, but have you assumed that the state omega obeys this cyclicity?
No.
Because it's coming out from this argument.
So you have to
coming out with this periodicity.
So yes, so the KMS condition tells you that it's periodic in imaginary time.
Okay.
Which is if you look at quantum mechanics or quantum statistical mechanics, that's the usual condition that is satisfied for a thermal state. It doesn't mean that you can commute the operators without anything else. So. Okay. Yeah. As I said, what we want to compute are relative entropies or relative things. So actually, we need two states. So one can redo the whole construction. Tomita operator, polar decomposition, given two states. So that means one takes A acting on one state phi and maps it to the adjoint acting on another state psi. So both should be cyclic and separating. And then the polar decomposition gives the relative modular operator and the relative modular conjugation. And by the same formulas as before, just now we have two states. And then the important formula that is important for the computation, so-called Araki formula, which relates the relative modular Hamiltonian, so log of delta phi psi, to the relative entropy. So one can show that in quantum mechanics, the relative entropy defined with the density matrices, as on the first slide, is equal to the right-hand side. But the point is that the right-hand side is also well-defined in quantum field theory, because the relative modular Hamiltonian is a well-defined operator there. So this shows also that this relative entropy is a finite quantity. It's independent of the UV cutoff, it doesn't diverge. An important case that has been studied in practice is when the states phi and psi are actually unitary excitations of, say, a vacuum, or a common vacuum state omega. So we have our state omega, might be the Minkowski vacuum. We take two unitaries, u and v, in the algebra, and two unitaries, u prime and v prime, in the commutant. And then we set phi to be equal u prime of omega and psi v prime of omega. It's not difficult to see that in this case, so just plugging these definitions into the definition of the Tomita operator, going through the computation, one sees that the relative modular operator is a unitary conjugation of the one of the vacuum. And therefore also the relative entropy is obtained by acting with unitaries on the vacuum and then take expectation value of the vacuum modular Hamiltonian. So as a summary, the relative entropy between two excited states, whatever this excitation is, relative to another state omega, which might be the vacuum, can be computed if I know only the modular Hamiltonian of the vacuum state. For example, one can look at coherent states. Let's say we take 3 of these unitaries to be the identity, and 1 to be e to the if, I phi of f. Then one can, what the formula gives you, the Araki formula, is the relative entropy between this coherent state and the vacuum, restricted to some region, and this region enters the construction of the vacuum modular Hamiltonian. This is what people have done and what I'm also doing. Okay. So now what is missing, what we need, is the modular Hamiltonian of the vacuum state omega, log delta omega. So let's look at some examples. Problem is that we only know some examples, only some special cases. The most important one is the so-called Bisoniano-Wichmann situation, which, as you can see, was done 50 years ago. And it's the case when we have the Minkowski vacuum state omega, and the algebra for Neumann algebra is the one that is generated by fields that are restricted to the right wedge. So if I've drawn you a picture here, the right wedge is the shaded region on the right. There's time and space. So my algebra, all the fields in this region. Everything that is space-like related, so the left wedge, that's my commutant. These things commute with the operators in the right wedge. And then, Bisoniano and Wichmann haven't phrased it in that language, but from their results, one can infer that the modular Hamiltonian is nothing else but the generator of boosts. So that means if I have a field localized in some region here, the boost, so the modular flow, will bring me up here, and the modular conjugation will map me into the others, into the left wedge. And this result is very important because it applies to arbitrary series, even interacting ones. So no matter what the interaction is, as long as it's local, so it satisfies the Weidmann axioms, this result applies. The downside is that the right wedge is, well, huge, obviously, it's infinitely extended. So it doesn't correspond maybe to a local measurement, so something that an observer would see locally. Okay, but it's an example. Another example, which was, well, computed just 2 years later by Buchholz, is, well, it's a very similar situation. We have the Minkowski vacuum state, but now the algebra is the one which is generated by free and massless scalar fields, restricted to the future light cone, with a tip at some point tau 0. And in this case, the modular Hamiltonian is a linear combination of time translations, so h, the Hamiltonian, and dilations. So things that dilate you along the light cone, which means that if you take fields in a region like here, you apply the modular flow, you get fields in a bigger region further up the light cone. And the modular conjugation maps you to a past light cone. So, well, this example is maybe a bit more physical because, well, let's say we as an observer can influence the things in the future light cone. That's fine. The problem is that it's restricted to a very specific theory, namely free master scalar fields. And the problem is, or the fact why this restriction appears, is because the modular conjugation needs to map you to the commuted of the algebra. And only if the fields are free and massless, they propagate on the light cone, which means that the fields in the past light cone inside commute with the ones in the future light cone, because everything propagates on the cone. So things up here, they interact with the ones outside here, but not with the ones in the past light cone. And then another well-known example.
Just before
yes?
you go on, the first example was this Rendler example, and
exactly.
Presumably the temperature corresponds to the periodicity corresponds to the Rendler temperature. I presume.
Yes.
The acceleration.
Yes.
Do you have a simple explanation for why the modular Hamiltonian is this boost operator?
No, sorry, no idea. I don't know. I mean, so saying that say the Rendler temperature is 2 pi is the same as saying that
there's an acceleration.
Yeah, sure, whatever.
The curve you have to pick.
Yeah, sure.
You have to choose the killing vector.
Of course. But no, so I mean, what I said before, one of the conditions on the modular flow is that the state is a thermal state. So in a sense, the Unruh effect is, let's say, a manifestation of this mathematical theory for this special case. But why it is that way, I have no idea. It just comes out like it.
Okay.
Okay, and well, last example in, say, higher space-time dimensions is the Hislop-Longo theorem, which came a bit later. So you see the papers from 82, and then 88, that's the PhD thesis of Hislop. Apparently the computation was a bit traumatic, so Hislop left the field afterwards and did something else. And in this case, again, we're in a Minkowski vacuum, but now the algebra is generated by 3 master scalar fields restricted to a diamond. So now it's really a finite region in space-time. Say a diamond has size L in all directions, and the center is at some point tau 0. And then the modular Hamiltonian is a linear combination of time translations, of dilations, and of special conformal transformations. So if you look at the modular flow, that means if you have fields in some region here, the modular flow maps it further up the cone, the diamond. And the modular conjugation does strange things. So it maps you partially in the future light cone, partially in the past light cone, and partially in some space-like separated wedge. You might wonder why all these conformal translations or generators appear. And essentially because the way they computed this result is by taking the Rendler wedge, the right wedge, and doing a conformal mapping to the diamond. So in this way, the boost generator gets mapped to this combination. And then one has to check that the modular conjugation fulfills the right properties. So it maps things into the commuted. This is now a very nice result because it's really a finite size region in space-time. But again, it's only for a very specific theory. So they derived it for 3 master scalar fields. It's not too difficult to generalize it to general conformal theories, but okay, our world is not conformal, so maybe one needs other examples. Let's see. There are other examples. There are many examples for 3 master fermions or conformal field theories in 1+1 dimensions. So, well, I put here some names. One can also compute the modular Hamiltonian for fields in the exterior Schwarzschild spacetime. There's a long list in one of my papers. Again, it's only for very special situations, and if you want to have massive fields, I mean, our world is massive, obviously, even if they are free, then the modular Hamiltonian becomes much more complicated. Something I did, well, with two collaborators a year and a half ago was to take a diamond, like in the Hislop-Longo result of size L, but in 1+1 dimensions, just to make computations easy, and to look at free fermions of small mass. Again, for the Minkowski vacuum state. So in this case, one can write down a general expression for the modular Hamiltonian. So it's just bilinear in fermion fields. Since we're in 2 dimensions, these have 2 components each. And then there's some integral kernel that needs to be determined. So this is an operator on a Cauchy on t equals 0 Cauchy hypersurface. And the results that come out is that, well, we worked for small mass, so essentially perturbation theory, starting from the masses theory. And the result is that for the diagonal components, so the 1, 1 and the 2, 2, this is a local term. So it couples the fermions at the same space-time point. And in fact, this one is exactly the result that you get if you use the general expression for a conformal theory for this special case. So that's a local transformation. However, the off-diagonal components, so the one that mixes the 2 chiralities, well, we have get a term proportional to the mass, and you see it's a horrible expression for the integral kernel. There is a local term, this delta x minus y here, that really keeps the fermions together and moves them essentially in a similar way as the local flow in the Hislop-Longo result. There's another term which couples fermions at opposite sides of the diamond. Again, it moves fermions like this. And then there are some non-local terms which are, well, they're well defined, but not very nice. So what one sees from this example is that the modular Hamiltonian in general will be a non-local operator. So for the cases before, it was always a local transformation, but in general, it will be something non-local. And this result generalizes some earlier result of well-known names from 2016, where they computed only the singular terms, namely the deltas, and this one here. Yes.
Sorry, I'm just wondering what the difficulty is with doing it more generally for a conformal field theory. I mean, the techniques for the free fields should not be that different than the conformal case.
Well, in the conformal case, you have essentially the same result as this one. So there's just the generators, of course, have a specific form depending on the concrete theory. But
it will probably depend on conformal weights or something like that, maybe.
Yeah, yes. So the action of D, for example, depends of K. They depend on the conformal weights.
It's going to be important in that, but this should work for an interacting theory then.
Of course, but conformal.
Conformal, yeah. I mean, you mentioned that it was restricted to a free theory.
Yeah, yeah. So this is okay. So yeah. So Hislop and Longo, they computed it for a free master scalar field. But if you look at their result, one can check that it applies to a generic interacting conformal field theory.
Okay, very good. All right, thanks.
But conformal. Our world is not conform. Yeah. Our world is not conformal.
I was confused as to what the difference.
Sorry. Yes.
Okay, that's fine.
Yeah. No, so for conformal theories, we know everything. That's fine. There's no problem. A massive field is not conformal. So then the problems start to appear. So if we want to apply it to real world examples, then we might get problems. It's still doable. It's just a long computation, at least for this case. Okay. So now we have our modular Hamiltonian. Now we can use it to compute relative entropies. So let's get to the second to last part of the talk, the zeta spacetime and relative entropy. I recall to you that the best way to look at the zeta spacetime in d dimensions is to embed it in the d+1 dimensional Minkowski spacetime as this hyperboloid that I've depicted here. So it's the Lorentzian analog of a sphere. And the relevant part for our universe is the expanding half, the Poincare patch. So that's the whole upper triangular part here. I've given you down the metric, it's probably well known. It describes both the primordial inflation and the current accelerated expansion of our universe. And the Sitter space is also a maximally symmetric solution of Einstein's equation. So it's not much more difficult than flat space, let's see. It has a lot of symmetry. The nice thing about the Sitter, you would think, okay, now let's look at modular Hamiltonians for the Sitter. We know it for the Minkowski spacetime, so maybe it's with this description of the Sitter, it's easy to also restrict it to the Sitter, and that's indeed the case. Namely, one looks at such a wedge here in dark gray. So this is just the intersection of the wedge, the Rindler wedge in the embedding Minkowski spacetime with the de Sitter hyperboloid. And the important point is that the generator of boosts in this wedge is tangent to the hyperboloid. So it restricts to an operator in the Sitter space. And then one has an explicit expression for the modular Hamiltonian, and one just has to check that it satisfies all the properties. So this was done for the situation by Borges and Buchholz. And indeed, it's exactly this generator of boosts. So this is very nice. And then one can compute the relative entropy, just using the formulas that I presented in the beginning. So what do? We take the Sitter vacuum, omega, Bunch-Davis vacuum, and the coherent state. So we take the Bunch-Davis vacuum and act with it with an exponential, e to the I phi of f. So what is this relative entropy? It is in fact the relative entanglement entropy, because we compare two states, and entanglement because we have restricted to this region A, which is the intersection of the Rindler wedge with the de Sitter hyperboloid. So it's this region in the coordinates. And the state that we look at is such that this function f is exactly inside this region. Okay, one plugs in the expression for the modular Hamiltonian. Short computation tells us that the relative entropy is equal to this symplectic product of, essentially commutator function applied to my test function f, and the commutator function applied to the boosted f. And of course, the symplectic product, one can just write down, it's an integral over Cauchy hypersurface of the corresponding conserved probability current. So the formula is here. It's well known, standard textbook material. Computing what this actually is leads us to the formula that I've given here. So the relative entropy in this case is given by, it's the right wedge. So if you look at the picture here, here the coordinate x1 in this direction. So in coordinates of the Poincare patch, it's x1 times some curly h. There's some other correction depending on some derivatives of f and also depending on time derivative, all evaluated on my Cauchy surface t equals 0. F hat is just the convolution of my commutator with the test function that I put in the coherent state. And the curly h is the Hamiltonian density, which I've written you down here. This is almost nice, almost because from general considerations, the relative entropy should be positive. But this expression is not manifestly positive. The first term is, because in the wedge x1 is positive and h as Hamiltonian density is also positive, but these two terms here in the end, they can have either sign. That's d1f, dtf, okay, whatever this is, it's not quite clear. Yes? No, okay. However, if we take the limit h to 0, so that means this term drops out, this term drops out, this becomes 1. We get exactly the correct flat space-time limit that was computed previously by Cassini and collaborators. What is the solution to this issue? Well, yes.
How restricted is this to free fields? Just
not at all.
The commutator function will it will change when you move to an interacting theory. There'll be some wave function or normalization at the lead.
Yes, it will. Also, the generator of the boosts will change because now you have to take the interacting stress tensor to define it.
But conceptually, the formula is rigid.
Yes, because the modular Hamiltonian, again, in this case, applies to even interacting series.
And the details of the theory are entering in the dependence of the boost generator on the fields and on the commutator function. Okay.
And this exactly.
That's quite generic then. So that's a generic formula that one can apply to essentially any theory.
No. So this formula here is again specific to free theory. If you're in an interacting theory, you get the sum of terms that would vanish for free theory. So the formula will be longer.
Okay.
But the Araki formula, so well, I have not written it down here yet. Let's go back to the slide. So we were using this formula here.
Yes.
So the version of the Araki formula for unitary excitation. This is completely generic.
Okay. All right. Thank you.
So this one could evaluate also for an interacting theory with the same log delta. So with this log delta here, and M01 is this expression. So that's fixed. Okay. So the solution to the puzzle that this is not manifestly positive is given by slightly modifying the evaluation. So instead of taking Cauchy surface t equals 0, we take a Cauchy surface of this form. So it's t equal to well, minus something that depends on x. And then we get a manifestly positive expression. Namely, we can write the result. So okay, there's a factor 2 pi. This is this usual 2 pi temperature. Some positive density q of f, and then a measure factor on this Cauchy surface. So this is just square root of minus a g on the Cauchy surface. What is this density q? It's, well, again, x1, because we're in the right wedge, normalized. And then it's the sum of squares. So there's a derivative of h in the normal direction of the Cauchy surface. There are some derivatives in the surface, so spatial ones. But this one is a positive definite matrix, so this whole term is positive definite. And then there's a mass term. So this is really manifestly positive. And we get a manifestly positive expression for the entanglement entropy. Moreover, this Q of H is nothing else but the density of the Noether charge for the boosts. So one can check that one takes the canonical stress tensor for a free scalar field, multiplies with the killing vector of the boosts and the normal vector of the Cauchy surface. And okay, there's a minus sign because of time orientation. And then one gets exactly this Q. So the Q is the density of the Noether charge of the boosts. And this general relation between an entropy and the Noether charge is something that was found also in previous examples. So for example, there's a paper by Wald from 1993 saying that black hole entropy is the Noether charge. So here we could say relative entropy in the sitter is a Noether charge. And also in a more general context, so if you are interested, there's a very nice lecture notes by Flörchinger. And we checked also that the relative entropy in this way satisfies some other nice properties that it should. So it's, for example, it's convex. If you take a linear combination of relative entropies for two different coherent excitations, and then the sum of these, that's always bigger than the relative entropy that would correspond to the sum of these excitations. Okay, very nice. But is this actually something that we can measure? You know, what does this have to do? What does this give us observationally? So what we actually have to look at are concrete observers in the sitter spacetime. So we know that not the whole Poincare patch is accessible to a single observer. So here a slightly different picture of the relevant parts of the sitter spacetime. This triangle here, sorry. Yeah. This triangle here would be the Poincare patch. But what is accessible to a single observer is only the shaded region here, or if you make it rotationally invariant, the diamond, which is a static patch. And one can write a static metric. The border of this patch is the so-called cosmological horizon. It's at r equal 1 over h. And the modular Hamiltonian is also known for the static patch. So it's just static time translations up to a factor of 2 pi over h, which is the sitter temperature. Yeah, so we again have this relation of the temperature of the region of spacetime that we look at with the modular Hamiltonian, just as in the Windler case. And well, this relation here was never really written down until 2 years ago. but the computations were done much earlier. I've put some references, as you can see. Okay, of course, the whole static patch is again very big. It's the one that an observer sees that lives for an eternal time, from past infinity to future infinity. So this is it's a too big region to look at actually. So what we want are small diamonds inside the static patch. And for this, well, this is a computation I did about 2 years ago, let's say. Again, one has to restrict to massless conformally coupled fields. Now there's a conformal dimension delta explicitly here that you can see. And what I looked at were small diamonds. We can here on the right-hand side, like this gray one or the shaded gray ones of size L inside the static patch. And in this case, the modular Hamiltonian, because it's a conformally coupled theory. So the modular Hamiltonian is a linear combination of dilations and special conformal transformations. And if you look at how it acts on the fields, there are two terms. So the first one is just the static time translations. So that would be the result for the full patch. And then there's a correction term. Yeah? So one subtracts something, mildly complicated. Here the delta enters the conformal dimension of the field of the operator O. And you can see that this correction term depends on the size of the diamond on L. So as the diamond becomes large, so that means as we go down here and recover the full static patch, this term goes to 0, so recover the right result. And with this, one can again now look at relative entropy. So for coherent state, again, well, computation is easy in conformally fed coordinates. This is the expression. So it's not very illuminating maybe, but for the fact that it's manifestly positive. So you can see it's again the sum of squares. And one is inside the diamond, so x is always smaller than L. L was the size of the diamond, x is small, so this is all positive. We checked that it's convex if you shrink the size of the diamond. So if you make it smaller, second derivative is positive. And this, in this special case, it's a verification of a general result that holds again for Tomita Takesaki theory for so-called half-sided modular inclusion. The idea is that if one has, say, the algebras of two regions where one is included in the other, then there's an inclusion of modular flows. So that is, one takes the modular flow of the bigger algebra of elements inside that stays inside. So in the context of relative entropy, that translates to the fact that it's a convex function of the size of the region. And okay, so now we have a nice small region accessible to an observer. We have the relative entropy. What can we do with this? Well, we can look at backreaction. We have our quantum fields here. This is where the function f has the support in a small region, a small diamond of size 2L inside the static patch. These things are massless conformally coupled fields, so they propagate on the light cone. At some point, the fields will reach the future cosmological horizon. They will pass the horizon via the semi-classical Einstein equations. They will backreact on the geometry and change the area of the horizon. So that means that we should be able to derive a relation between the entropy of these fields here and the change of the horizon that they engender when they propagate. For the practical computation, instead of taking the Cauchy surface eta equal constant, which would be a Cauchy surface here, one deforms the Cauchy surface until the horizon. So when we get the expression that the relative entropy between the Bunch-Davis vacuum and the coherent excitation is given by some integral over a component of the classical stress tensor for a classical excitation F. And then we use the Raychaudhuri equation to relate the change of area of this null surface here of the cosmological horizon with the stress tensor. So this tells us in this specific case that the UU component is exactly the change of the geodesic expansion of the horizons, of the change in area, with the parameter u, which is one of the null coordinates. And then one does the computations, and it results that the relative entropy, in this case, is exactly equal to 1/4 g times the average change of area. of the cross-sectional area of the horizon. So of course, the factor 1 over 4g is well known, Bekenstein and others. But the important point here, I would say, is that this is an equality between quantities which are well defined without any UV cutoff. And this is a relative entropy, it's a finite quantity. And the change of area of the horizon is also a well-defined quantity, independently of whether the horizon itself is infinite or not. And of course, it's very nice that we find exactly the same proportionality factor 1 over 4g at leading order. This is semi-classical Einstein equation. Okay, so that's the entropy-area law that I promised. And then as a very last thing, we also looked at the local temperature. So as we know from say classical thermodynamics, there's a relation between energy, entropy, and temperature.
Just out of curiosity, is there any secret to why it's 1 over 4 in this case as well?
It comes out of the computation.
There's nothing obvious.
No, there's nothing obvious. No.
You just have to do the computation, and 1 over 4 just pops out.
I think so, yeah. If you want to have a look at the paper, the computation is in more detail. Maybe you find something obvious where it's clear, but at least for me, it wasn't.
Okay, all right, thanks.
So, yeah, as I said, in the very last step, let's look at an actual observer with some proper time t and some for velocity, who is crossing a Cauchy surface in our de Sitter spacetime. So it means that the velocity restricted to the Cauchy surface is exactly the normal vector of that surface. This observer measures the relative entropy, the one I've written down 2 slides before, this one here, on the Cauchy surface at the equal constant. It's exactly the contraction of the classical stress tensor with the corresponding conformal killing vector and the normal vector integrated over the Cauchy surface. So we can view this term here, the integrand, as an entropy density. It's the local density of relative entropy that the observer sees. And of course, the observer also sees an energy density, which is nothing else but the stress tensor contracted with 2 for velocities. Now, comparing the explicit form of the conformal killing vector with the for velocity and using the first law of thermodynamics, which tells us that a change in entropy density is equal to beta times the change in energy density with inverse temperature beta, it follows that the inverse temperature beta that the observer sees, that the observer really measures when he crosses this Cauchy surface, is given by the derivative of the proper time of the observer with respect to the modular flow parameter tau, or the negative one, which is defined by writing the conformal killing vector as a derivative with respect to tau. Now, this is exactly the result that was postulated by the thermal time hypothesis. Well, let's put some names here. This is what, 20 or 25 years ago. And if then one plugs in the result that we had before and computes this inverse temperature beta, this is the result. So there's a 2 pi over h. This is maybe the well-known temperature of the de Sitter static patch. But then there are corrections. So there's a 1 minus something exponentially decaying. And this depends on the static time of the observer. So there's a t tau minus t min. And the t min is the static time that corresponds to the lower tip of the diamond. So if I go back to one slide, we have an observer that starts somewhere here, goes to the future. Then t min is the static time of this point here. T tau is the static time of the observer somewhere here in the middle. And we see that the temperature that the observer measures exponentially fast approaches the, say, equilibrium temperature of the static patch. Also, if we take the diamond now very large, we cover the static patch, so everything is very consistent. But the thing that this result tells you is that the temperature of the static patch really has an operational interpretation. It is really the temperature that an observer measures. Just like the Rindler temperature is really the one that you would measure with an unreal detector. Of course, if you are, well, I said, if you have a finite size diamond, then there's some subleading corrections, but essentially you get 2 pi over h. Okay, and then I'm finished. And if you have further questions, I'm very happy to answer.
Thank you very much.
Yes, thank you very much.
Maybe I'll ask something. So you said that you don't need a UV cutoff to get this finite relative entropy, but would anything change if you did have one?
Probably, yes. You would get some terms that would vanish with the UV cutoff going to infinity. Yeah. But the UV cutoff is just a computational tool, and nature doesn't have a UV cutoff, or at least not until we have a theory of quantum gravity. So if you can give me a theory of quantum gravity that has a UV cutoff, then there should be corrections to this, proportional to this cutoff, or 1 over the cutoff. Yes.
I have a question about the choice of the hypersurface. You said that when you calculate the relative entropy on this t is equal to 0 Cauchy surface, you find that it's not positive.
Not manifestly.
Okay, right.
So since the symplectic product is independent of the choice of the Cauchy surface.
Yeah, okay, right.
This thing is the same as this expression.
Yeah,
it's just that here we can. It's just that here we can see that it's positive, and here we cannot see it directly. It's not manifestly positive.
Yeah,
but they're actually the same. It's the same quantity. Yeah.
Yeah, what I wanted to check. Yeah, that makes sense. Thank you.
Okay. Yes.
So I mean, your computations relied very heavily on the symmetry of de Sitter space.
Yes.
You could have used other states on de Sitter space that are some non-Hadamard vacua, which they're often called alpha vacua. Which it should be possible to do computations in that setting as well. But would there be something interesting in that? I mean,
I don't know. So the main problem is that
there's some of those that the main difference is that in those alpha vacua is that they have a slightly different charge or a slightly different parameter in front of the local Hadamard term, the divergence of the Green's function goes to 0. Except for one of them, which puts a singularity at the antipode. They also have singularities at the antipode. Would there be some physical sense in which, since you're using this Poincaré patch, I'm not quite sure what boundary conditions you need to put at the other end, and why I should pick out that particular de Sitter invariant state.
Right. Okay. So the main problem is that if you don't take the Bunch-Davis vacuum, but one of these alpha vacua, it's not clear what the modular Hamiltonian is. So the modular Hamiltonian depends on a state and the region. So even if the region is the same, if you change the state, the modular Hamiltonian will change, and no one knows what it is for an alpha vacuum. So then already the start of the computation doesn't work. But I mean, a bigger problem is that these alpha vacua, they cannot be generalized to interacting series, at least not in in a nice way. You run into all sorts of pathologies. So I think they are really just an artifact of free theory in that case.
Yeah, I think one of them can be generalized. The one where you preserve the charge, where you preserve the property, local Minkowski, but you put an additional singularity at the antipode.
No, but all of them have singularities at the antipode.
They do, but
all of them are singularity at the antipode.
Only one of them preserves the Hadamard property. Only one additional one.
Yeah.
Correctly.
An additional one. Okay. So I thought that only the one with alpha equals 0, which would be the Bunch-Davis vacuum.
I think there's another one. It might be alpha equals -1,
Okay.
something like that.
Okay. Well, that would be interesting to see. So then the first thing to do would be to compute this modular Hamiltonian.
Okay.
And then one could continue the computation of relative entropies.
Okay.
Yes. Okay, yeah. Would be an interesting thing to do.
Just one other question. Maybe I should wait until after the recording has stopped to ask it.
Okay. Okay.
I can stop it now.
Unless there are other questions.
Doesn't seem so.